This is lecture 5E. We've been talking about gas laws, specifically the ideal gas law equation, and I want to end up this chapter with a definition of an ideal gas. An ideal gas is a hypothetical gas that obeys the ideal gas laws perfectly. All this time we've spent talking about PV equals nRT, Avogadro's law, Boyle's law, Charles' law. It turns out that real gases do not obey each of those mathematical relationships completely accurately. The only thing that does is something called an ideal gas. And an ideal gas is described by a couple of specific assumptions of the kinetic molecular theory. If you remember the kinetic molecular theory of matter, it assumes that matter is made up of small particles that are in constant motion. So if you have a gaseous substance, then if we assume those gas particles have no attractive forces between them, and the gas particles are actually point masses that are in constant motion, then we would have something called an ideal gas. Now, the second point here, the gas particles are point masses. Let's define what that means. Back in geometry, you learned what a point was. You probably learned it the first day of geometry, where the first page of the textbook describes a point, a line, and a plane. A point is a representation of a region of space. How big is a point? A point is infinitesimally small. It actually takes up no volume. So an ideal gas is actually a gas that's made up of gas molecules, but we assume the gas molecules are so small that they do not take up any space. And our first assumption here, we assume the gas particles do not attract each other, which is actually not true either, because gas molecules attract each other with at least London dispersion forces if they're nonpolar. They would also have dipole-dipole attractions if they were polar. So real gases do not exactly obey the gas laws. The real gases deviate from ideal behavior because of two reasons. First, molecules actually do attract each other. Now, what effect does this have? This actually has an effect on the pressure of a gas. Here are 4 gas molecules in a container, and if this were a video, they would be moving around in straight line motion, banging into the inside walls of the container, exerting a pressure. If we focus in on the red gas molecule, when that red gas molecule hits the side of the container like that, that causes the phenomenon known as pressure. If the molecules don't attract each other, that red molecule hits the side pretty hard. But what if the molecules do attract? They don't have really strong attractions, but they do have some attraction. So what's going to happen to that red molecule as it bangs into the wall now? Because of this back attraction, it's not going to hit the wall quite as hard. If all the molecules are not hitting the walls quite as hard, the measured pressure will be lower than what it would have been if there weren't any attractive forces at all. So this always causes an observed pressure or a measured pressure of a gas to be less than what the pressure would be for an ideal gas. This causes deviations in our ideal gas law equation. A second reason that real gases deviate from ideal behavior is because the molecules themselves take up space. If those 3 molecules in this container were ideal gas molecule particles, they would take up no space because they would be points. That red molecule could be anywhere it wants to in that entire square container. But because real gas molecules do take up space, the red molecule cannot be any place it wants in the container. It can be any place in the container except the bottom left-hand corner where those 3 little green molecules are. So this means that because the molecules take up space, it causes the volume that's available to each real gas molecule to always be less than the volume of the container. So when we look at the ideal gas law equation, PV equals nRT, it really means the pressure when there's no molecular attractions, multiplied by the volume when the gas molecules take up no space. Those will multiply together to make nRT. This works perfectly for an ideal gas because ideal gases have no molecular attraction and the particles don't take up any space. Well, this is not true. So if we want to use an equation similar to the ideal gas law equation for real gases, we need to make some corrections. And Johann van der Waals came up with an equation that corrects for these 2 deviations. And let me show you his equation and see if we can explain what these deviations are. When you measure the pressure of a real gas, and I've got that labeled as P submeasured, that pressure is always going to be lower than what the pressure would be for an ideal gas. So what van der Waals has done is he's added a fudge factor, that A multiplied by N over V squared, to boost the pressure of the measured gas so it'll be a little bit larger value, so it will eventually equal what the pressure would be if there was no molecular attractions. In his second term, V minus NB, V is the volume of the container. We always assume that's the volume available to a gas, specifically the volume available to each gas molecule, but that's not really true because some of the molecules take up space. So what van der Waals did is he subtracted this term NB, another little fudge factor. That's the space taken up by the molecules themselves. So if you take the container volume minus the space taken up by the molecules themselves, that's going to give you the volume available to each gas molecule. This is the corrected ideal gas law equation, and it's called the van der Waals equation. It has two green values in the equation, A and B. Those are called van der Waals constants, and those are numbers that have to be determined for every different type of gas. Carbon dioxide has an A and B value, nitrogen has an A and B value, helium has an A and B value. Every single gas would have its own specific van der Waals constants. The A is the one that's in the pressure term. That's the correction for the fact that the measured pressure of a gas is always going to be too low because molecules are attracting each other. So if you have molecules that have really, really strong attractions, you have to add a really big fudge factor. That means A has to be a big number. So A is related to how strongly the molecules attract. The more they attract each other, the more you have to correct. So A has to be a bigger value. So what this A term does, the A multiplied by N over V squared, is it increases the measured pressure of the real gas, which is P, so that it equals the pressure of an ideal gas, which is what's in our brackets. The second van der Waals constant, B, corrects the container volume for the fact that molecules themselves are taking up space. So if you have really, really big molecules, they're going to take up a lot of space in the container, so B has to be a big value, so you subtract out all that big volume of the molecules. So B is directly related to the actual size of the molecules themselves. So this B term in the equation decreases the volume of the container size, which is usually just V, so that in parentheses, V minus N over B equals the actual volume available to each specific gas molecule. So let's see the effects of using a van der Waals equation in trying to describe something like the pressure of a gas as opposed to the ideal gas law equation. We're going to calculate the pressure of 1.000 moles of ammonia gas at 0.0 degrees Celsius in a 22.42 liter container. If we use the ideal gas law equation to see what the pressure would be calculated to be, we would isolate P by dividing both sides by V. And if we plug the numbers into the right side of the equation, it's 1.000 moles, the universal gas constant, multiplied by the Kelvin temperature of 273.2, and divided by the volume of 22.42 liters. Moles, liters, Kelvin cancel out, and our answer comes out in atmospheres. So from the ideal gas law equation, we would predict this gas should have a pressure of 1.000 atmospheres. That assumes that the gas molecules do not attract and they do not take up any space in the container. So let's try making the same calculation with the van der Waals equation instead. If we're going to use the van der Waals equation for ammonia gas, we have to look up the A and B values for ammonia, which they can be found in chapter 5 of the textbook. You can certainly look them up online as well. Here are the A and B values for ammonia. So if we want to solve the van der Waals equation for the pressure, the observed pressure, which is P, I have to isolate P in this equation. Algebraically, the first thing you do is, because we have two terms on the left side of the equation that are multiplied by each other, that's what terms are, or actually two factors, I should say, not terms. I have this factor multiplied by this factor. We have to get rid of this factor first from the left side of the equation before we can isolate P. So I'm going to divide both sides by the factor V minus N over B. And that's going to leave P plus A times N over V squared on the left side. And the right side becomes nRT over V minus NB. Now I have two terms on the left side, two things that are separated by an addition or subtraction sign. And to get rid of the A times N over V squared, I need to subtract that from both sides of the equation. So if I subtract it from both sides of the equation, the pressure of a gas based upon the van der Waals equation will be nRT over V minus NB, then minus A times N over V quantity squared. So we just have to plug all the numbers now into the right side of that equation. And so I'm going to need the whole page to do it. N is 1.000 moles multiplied by the universal gas constant multiplied by the temperature 273.2 divided by the volume of 22.42 minus our fudge factor, 1 mole multiplied by the van der Waals B constant 0.03707 liters per mole. Then the second term is the van der Waals constant A multiplied by the fraction 1 over 22.42 liters squared. And we're going to then multiply each of these out, then subtract them. In terms of the units, on the left term, the moles, the liters, the Kelvin cancel out. And so do the moles. And what do we have left over here? We have left over atmospheres in the numerator. So this will be atmospheres. And the answer comes out 1.001 for significant figures with a guard digit 6 atmospheres. For my second term, I have liters squared canceling out, and the mole squareds cancel out because the mole is squared in that parentheses. And that leaves atmospheres as the units, and this will be a 4 significant figure number as well, 0.008295 and a guard digit 9 atmospheres. When we subtract these, the pressure comes out to be 0.993 atmospheres. So the pressure of the gas from the van der Waals equation has been calculated to be lower. We would expect that because real gases always have lower pressures than ideal gases because the molecules attract each other. And in fact, if we do measure the pressure of ammonia gas under these conditions, this is the pressure we would get. This is very accurate. So how big of an error is this? It's 0.007 atmospheres smaller than what the ideal gas law equation predicted, and that's 0.7% error. So as a chemistry student, you have two choices. You can go, gee, do I want to have a perfect calculation of the pressure of my ammonia gas and spend 5 minutes doing this calculation that we just did here? Or do I want to spend 30 seconds and do PV equals nRT and accept less than 1% error? Generally, chemists accept the less than 1% error and use the simpler equation as opposed to the van der Waals equation. But if you need things calculated accurately for properties of gases, pressure, volume, quantity, or temperature, then the van der Waals equation will actually correct for the two major flaws in the ideal gas law equation: the fact that molecules actually do attract each other and the fact that they take up space themselves. To finish up the chapter on gases, I want to spend a little bit of time now talking about atmospheric chemistry. And there's a couple of things that occur in the atmosphere that are probably things worthwhile for you to know. We actually burn a lot of hydrocarbons on this planet, and that's how all of our cars run, unless you have a Tesla or something. So combustion of hydrocarbons from automobiles has an effect on our atmosphere. When you burn octane in your car, the octane's reacting with oxygen that your engine sucks in from the air, and it combusts it into carbon dioxide and water vapor. This produces a significant amount of heat, but it produces, more importantly for your car engine, a higher pressure. And we'll talk about in the next chapter how that increased pressure actually causes you to get work done by your car and allows your car to drive. But nonetheless, this is the reaction that occurs, and it occurs at a high temperature because when anything burns, it's always really hot. Well, you're not only sucking oxygen into your engine, but you're sucking all the other components of air into your engine as well. And because it's such a high temperature and you're sucking the nitrogen gas from the atmosphere into the engine as well, you actually get some of the nitrogen gas to combust inside your car engine also. So when the nitrogen combusts, it turns into nitrogen monoxide. And then that nitrogen monoxide will actually combust further with more oxygen and turn into nitrogen dioxide, which is a gas we've seen before in lab. That's that poisonous orange gas that's given off when concentrated nitric acid exists as an oxidizing agent. Did you know that you were giving off nitrogen dioxide gas from your cars? Have you ever seen pictures like this? Los Angeles basin there, that nice haze of orange that settles over the entire valley? That's nitrogen dioxide that's produced from the combustion of octane in our car engines. It's pretty at sunset, but it's actually kind of rough to breathe. That nitrogen dioxide, if you were in lab and you had a chance to breathe any bits of that vapor, it's a choking gas in higher concentrations, completely poisonous. Now, what happens is when this nitrogen dioxide is produced in our atmospheres or in cities, and the light comes out during the sun shining part of the days, during daytime, I could say, that's probably a better way to say it. What happens is the nitrogen dioxide gets decomposed by visible light into nitrogen monoxide and an oxygen atom. And that oxygen atom has 6 valence electrons, an incomplete outer shell, and that's very reactive. We have a name for anything that doesn't have a complete octet configuration. It's called a free radical. Maybe you've heard of that before. You don't want to eat things that produce free radicals in your body because they're very reactive. They can react away with biological molecules in your system. So this oxygen atom is called an oxygen radical or a free radical, and it's very reactive. So what it'll do is if it bumps into anything else, like maybe an ozone molecule, it will turn into ozone. And so we actually produce ozone whenever there's orange smog produced from running of car engines. And it's the ozone that actually, when it then dissolves in the moisture of your eyes, that causes irritating and eye difficulties. So the combination of the orange gas, nitrogen dioxide, and then the created ozone when sunlight appears, we call this photochemical smog. There have been improvements in car engines where they wind up running at lower temperatures than they did in the old days. I mean, Los Angeles looked like this all the time back in the 1980s and 1970s, but it doesn't look like that way anymore. In fact, my brother lived in Pasadena in the 1970s for a while. When he first moved there, it was always so smoggy. One day they had Santa Ana conditions, and the Santa Ana winds blew all the smog out, and he looked up. He was living less than 1 mile away from the giant San Gabriel Mountains. He had never known they existed. It'd be like you living in Santa Margarita, and then one day going, oh my gosh, Saddleback Mountain is right there. I never even knew that. So we don't see this anymore because car engines now run more efficiently at lower temperatures, so they don't burn as much nitrogen, and so we actually don't get this photochemical smog. So improvements have been made, and the old days when in cross-country practice we'd have to be canceled because the days were too smoggy, and that would happen every once in a while, even in Irvine and Orange County, not anymore. Second thing I want to talk about is production of electricity from coal-burning power plants. We have a lot of electricity produced by the combustion of coal. Coal is mostly carbon. And so when they burn the coal, it turns into carbon dioxide, and it produces a bunch of heat, and that heat is used to boil water, and that water causes a turbine to spin, and that creates electricity for us. Well, most coal contains elemental sulfur. And so when you start burning this coal, and carbon dioxide is released from the high chimney stacks in the coal burning power plants, because sulfur also exists in the coal, you actually burn the sulfur as well. And so when this sulfur burns, it produces sulfur dioxide gas, which is a bit of a choking poisonous gas as well. It just doesn't have a characteristic color to it. This sulfur dioxide can further oxidize or further burn with more oxygen to produce sulfur trioxide, which is a really dense white colored gas that's really poisonous and hard to breathe. Really bad for you. It causes you to choke for sure. Now, when this sulfur trioxide is produced from the burning of coal and is released into the atmosphere, if it comes in contact with any moisture at all, the sulfur trioxide can dissolve in that moisture and form sulfuric acid. This is very similar to what happens in sodium hydroxide solutions we use for titrations. If they have carbon dioxide dissolved in them, what does the carbon dioxide do when it dissolves in water? It turns into carbonic acid. Non-metal oxides, when they dissolve in water, become acids. So sulfur trioxide, when it dissolves in water, also becomes an acid. It becomes sulfuric acid. And where would sulfur trioxide run across water molecules in the atmosphere? In the clouds. And so the clouds wind up creating little droplets of water that have sulfuric acid in them. And when they drop those droplets of water, that produces acid rain, which is really bad for lakes and streams and statues. And so that was a big problem also in the 70s and 80s. And they came up with a way to try to mitigate that. In those tall chimneys in the power plants, they now have a compound calcium carbonate added to the stacks of these coal-burning power plants. So way up there in those stacks, tons of calcium carbonate is placed. As coal is burning and the temperature gets really hot in those chimneys, the calcium carbonate decomposes into calcium oxide and CO2. And it's the calcium oxide that's important, because when sulfur trioxide moves up the chimney and encounters the calcium oxide, first the sulfur dioxide actually, before it has a chance to turn into sulfur trioxide, the sulfur dioxide combines with the calcium oxide to form calcium sulfite, which is a solid. So that means the SO2 is essentially precipitated out of the gas and turns into a solid, so you don't release the sulfur dioxide into the air, so it doesn't turn into sulfur trioxide, and so you don't get acid rain, and we no longer have big problems with acid rain any longer in this country. This process is called scrubbing because they're cleaning the exhaust gas by scrubbing out all the sulfur dioxide of it by using that calcium carbonate. The final point I want to talk about, oh no, two more. The third point I want to talk about is stratospheric ozone. We have ozone that exists in our atmosphere at a layer about 15 to 50 kilometers above the surface of the Earth. At sea level, ozone's no good for us because it burns our eyes. But up in the upper atmosphere, it has a really important use. That ozone absorbs ultraviolet radiation that's constantly being given off from the sun. And the way it works is the ozone molecules in the upper atmosphere will absorb a photon of ultraviolet radiation, which is high enough energy, it causes the ozone molecule's chemical bond to break, turning it into an O2 molecule and then a free radical oxygen atom. That oxygen atom will eventually bump back into another O2 molecule and recombine to form ozone. But when it does, it gives off several low energy photons of infrared radiation. So the ozone is essentially turning ultraviolet radiation from the sun into infrared radiation, which is low energy, just heat. And so the ultraviolet radiation never makes its way down to the surface, at least a high percentage of it doesn't. So that's significantly important because if the ultraviolet radiation reached the surface of the Earth and you walked outside and looked up, an ultraviolet photon would strike you right in the forehead. And when it did, it has enough energy to break a molecule's bond in one of your cells. And a lot of ultraviolet radiation photons could break a lot of little molecules in one of your cells. And if they break too many molecules in one of your cells, that cell could die. And if that happens to a lot of cells, you could actually have an organ failure. And if that happens significantly in your body, then you as a living organism would die. So ultraviolet radiation is not good for any living organisms on the surface of the Earth. So it's good that the ozone is absorbing those. Well, back in 1974, I was in Chem 1A, and my instructor was Sherwood Rowland. And Dr. Rowland came in one day, and he had a really low voice, and he said, "I'm going to have to leave for a week. I'm going to Washington, D.C., because I have to talk to the Senate, because I do believe that compounds that we're using in our refrigerators and our air conditioning units are destroying the ozone layer on the planet, which could destroy all of humanity." And we were just in utter shock at how serious that sounded. So what Rowland had done is he had been doing research on propellants they use in spray cans. And these propellants were also used as coolants in refrigerators and air conditioners. They were called chlorofluorocarbons, CFCs. And he found that these were really stable molecules and they would last in the atmosphere for a very long time. And what they would do is if they moved their way up to the upper atmosphere where the ozone is, they would interact with ultraviolet radiation, breaking down to release a chlorine atom. And that doesn't have a complete outer shell, so it's very reactive. It's called a chlorine radical. So what would that chlorine radical do? Rowland found that the chlorine radicals were bumping into ozone molecules and turning them into an oxygen molecule and a CLO molecule. That CLO molecule has an odd number of electrons, so it's a free radical also. That CLO molecule then would eventually bump into an oxygen atom, forming O2 and a chlorine atom. And this process now, because it produces that chlorine atom right here, that chlorine atom will go back, bump into an ozone, turn it into an O2 and a CLO. The CLO would then bump into an O, turn it into an O2, do a Cl again, and that process would repeat itself approximately 1 million times before randomly 2 chlorine atoms combine together to form a more stable chlorine molecule. So every single chlorofluorocarbon molecule that comes from air conditioners, refrigerators, and spray cans that moves its way into the upper atmosphere, Rowland found was destroying about 1 million ozone molecules. And they noticed this from measurements they were taking around Antarctica. During the dark months of winter in the southern hemisphere, so that would be June or July, these chlorine radicals that were being produced from the chlorofluorocarbons would accumulate on the surface of ice clouds over Antarctica. The whole way this works is actually important or related to the geology of our planet. Antarctica is a continent and it's over the South Pole, and Antarctica has not always been over the South Pole because the continents have been moving. But when Antarctica eventually moved over the South Pole, it caused a big change in the wind patterns on our planet. When you have a land mass over one of the poles, then winds start to funnel, and they funnel south all the way around down to Antarctica, and these winds circle Antarctica. So the chlorofluorocarbons creating the chlorine radicals would have them eventually accumulate down by Antarctica, and they would then freeze up in these ice clouds. As winter ended each year, and winter ends in about August, and sunlight comes out, that would free up the chlorine radicals, and Rowland was able to measure that the amount of ozone in the atmosphere above Antarctica would decrease rapidly in the month of August, and that's because these chlorine radicals were being released in August each year. They would react away as many ozone molecules as they can until they were gone, and this whole process would start the next year as chlorofluorocarbons were producing chlorine radicals. They would freeze in the clouds, and then the next year on the next August, the same thing would happen. And measurements that were made showing what the ozone content was on the Earth above Antarctica at different months is shown here in this graph, where the more red the color is, the higher the ozone concentration, and the more purple it is, the lower the concentration. So in July, in the very first picture, you can see around the equator, it looks like the ozone concentration is about 330 to 440 Dobson units because it's kind of green in color. But around Antarctica, it's maybe about 250. So naturally lower down there because the chlorine radicals get pulled there. So they're going to react away some of the ozones. But as soon as the sun comes out in August, then all of a sudden the chlorine radicals start reacting away with the ozone molecules, and the amount of ozone drops drastically below 200 down to maybe 150 Dobson units. And it stays that way for a couple of months until the chlorine radicals have all reacted away. And then the ozone layer starts building itself back up again. And this whole pattern repeats every year. And successive years were showing that this decrease in the amount of ozone over Antarctica was growing. And they called that the ozone hole. And so Rowland went to Congress and talked about this problem, and the United States government decided that we need to do something about this, and so they decided to ban chlorofluorocarbons from refrigerators and from air conditioners and from spray cans, and industries came up with alternate molecules they could use for these processes. So we no longer use chlorofluorocarbons anymore. They've been banned now for 30 years, essentially. And as we monitor the amount of ozone over Antarctica, we can see that the ozone hole has stopped growing, it's leveled out, and it's actually starting to come back. And not the hole's coming back, but the amount of ozone during the summer months is coming back. And they predict in 40 to 50 years from now, the hole in the ozone layer below and above Antarctica will actually be gone, and we'll be back to a planet that has a fairly decent amount of ozone, and we won't have this problem anymore. But even now, I mean, it's significant. If you live in New Zealand or Australia, which is much closer to Antarctica than we are, right? Those people are really sensitive about getting skin cancer from a decreased amount of ozone above them. And you go to the beaches and everybody's got that white zinc oxide or titanium oxide on their nose, where like you wouldn't see anybody wearing that here in California because you wouldn't be cool, but everybody does in Australia because they don't want skin cancer because of the decreasing amount of ozone. Rowland wound up winning the Nobel Prize for his work. And so I had the honor of having a Nobel Prize winner as my Chem 1A teacher. And then you just got me. So what can you say? This is this leads to one other interesting story about this. I was at Irvine High School teaching for a number of years. And I was in charge of the academic decathlon team at Irvine High School, where we would compete against other schools in like 10 different academic areas: science, math, English, writing a paper, giving a speech, blah, 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 lots of things like that. They wanted to start an academic decathlon team back in the 90s. And so the principal called me in and asked me if I would do it. I said, sure. And so they said, we'll send you over to University High School. University High School is right next to UCI. It's also in the city of Irvine. I was at Irvine High School, so we're rivals. And University High School, being close to University UC Irvine, had a lot of professors living around there, and the students tend to be pretty talented there. And in fact, every year when they were announcing national merit semifinalists, University High School would have like 30 national merit semifinalists, and our high school would have like 3. And so definitely a lot of smart people lived around there. And so I went over to talk to their academic decathlon coach. Her name was Carol Jackson, the AP English teacher at University High School, one of my 2 mortal enemies of my life. And I walked in there and I said, I've been sent over so I can talk to you about how you run your academic decathlon team. And she said, well, I'll be happy to tell you, but of course, you certainly can't expect to compete with us in the academic decathlon. And with that statement there, I thought, boy, it really should be my life's mission to beat Carol Jackson in the academic decathlon, because I thought it was really rude and condescending to say. And so we put together our little academic decathlon team, and we eventually, I started with freshmen and sophomores. So 2 years later, we eventually had a team with seniors. And so we were competing against University High School, and we had worked our people really hard. And they always have one category that's called the super quiz. It's always on something completely different than regular academic categories. And in this particular year, it was on in the environment. And I had one of my AP chemistry students competing on the team. And this last event, this super quiz event, they would put all the students down on the floor of a gym, and everybody in the stands, then all the spectators and fans and parents and stuff would be there, and they'd watch them answer these last questions of the academic decathlon. And so we had our students down there, all the students were there, and the question came up: what is the chemical that's responsible for the depletion of the ozone layer on Earth? And I thought, oh, I've got my AP chemistry student down there. We just talked about stratospheric ozone in class. There's no way he's going to miss that question. And he got it wrong. And each of these super quiz questions were worth 100 points. So we lost 100 points there. So 3 weeks later, we go to this, they have a big awards ceremony. It's a dinner, and they're announcing the top schools in all of Orange County. And it turns out that we were in the top 5 in Orange County. So was University High School. We lost to University High School by 99 points. So that one question, if he would have gotten it right, we would have beaten them, and I would have stuck it to Carol Jackson. And because I didn't, I still can't stand Carol Jackson, and that still bothers me. The student that missed the question, though, I really liked him. He was a great guy. It's too bad it happened. He actually went on to become a chemistry professor, and he's now teaching at the University of Wisconsin. So I mean, things worked out for him, but still unable to get over that. So every year I put on my test: what is the gas responsible for the destruction of the ozone layer on Earth? And if you miss it, you will lose 50% of your test score. So don't miss that question when it's on test 5. The last thing I want to talk about is greenhouse gases. And greenhouse gases are gases that absorb infrared radiation from the sun, trapping it in our atmosphere. We have gases in our atmosphere that do this. Water is the strongest greenhouse gas that's in our atmosphere. Methane is second. Carbon dioxide is actually pretty low. But it was Svante Arrhenius that predicted back in the 1890s, when the Industrial Revolution was starting, that if we start burning too much carbon-based material, we're going to produce a lot of carbon dioxide, and that could actually warm up the atmosphere here. And we have, since the time of Arrhenius, we've had 125 years of scientific observations, and scientists have predicted, that an increase in these greenhouse gases could result in things that are catastrophic. You could have glacier melting, sea level rise, and even more powerful storms because of that. So during your lifetime, people have tried to adopt benchmarks to try to prevent this from happening. And the widely adopted benchmark needed to try to avoid these worst effects of global warming would be to try to reduce the global temperature rise over the next 100 years from a predicted 3-degree temperature rise over 100 years to only a 1-degree temperature rise over 100 years. From 1900 to 2000, Earth's temperature rose 1 degree Celsius. We're able to handle that. From 2000 to 2100, it's thought that maybe the temperature of the Earth may go up by 3 degrees, and if it does, that would cause some of these dire consequences that are in the paragraph before. But if we can only make it go up 1 degree as well as it did this last century, then we'll avoid a lot of these really catastrophic things from happening. And so when you were a little bit younger, 5 years ago, in 2015, the Paris World Climate Summit was held, and it proposed the world's most ambitious climate policy in order to cut carbon dioxide emissions. It was called the Intended Nationally Determined Contributions, or INDC. And what it essentially was a policy that would try to cause countries to reduce their use of fossil fuels. And if the US were to follow the INDC policy, that would actually be a charge to everybody. The net cost to the US would be about $250 billion a year for every year for the rest of the century. So that would be $833 per person per year for the next 80 years. Now, the United States pulled out of the Paris World Climate Summit agreement, so we're not doing this, although the state of California is, so you're actually paying that. That's why your gasoline is at least 50 cents higher than any other state anywhere around us. Sometimes it's even $1 higher. This has actually been put into effect by the government of California, and so we're actually working towards this, where we're trying to raise that money in order to prevent people from wanting to use fossil fuels so much. Now, what's going to be the effect of that? Because you're paying it, and you're going to pay it every year for the rest of your life, I believe. So if every country in the world exactly fulfills the promises they made to the INDC for the period 2020 to 2021, then if the entire world does what California is doing, the reduction in the global temperature rise will be 0.17 Celsius degrees. So you have to think about what we wanted. We wanted the temperature rise to drop from 3 degrees to 1 degree. If we do everything that this policy says, we're going to cause it to drop only 0.17 Celsius degrees, which is not very much. And in fact, it would essentially delay the global warming by just 4 years. So in 2100, the temperature rise would not have been quite as much as they would expected, but 4 years later, the temperature rise is exactly what it is. So for those of you that are environmental science majors, I want you to save the planet, make sure that people and animals and plants are healthy. We are good shepherds of the planet we live on, but I wanted to use common sense in coming up with ideas to make this a better place. And I really don't see how $833 per person per year for the next 80 years in order to delay global warming by 4 years is actually a good policy. And it turns out that actually only 2 countries in the world are actually fulfilling that promise right now. So there's no way it's even going to be a 0.17 Celsius degree decrease in global temperature rise unless something significantly different changes. Now, some good news here. The IPCC, which is the Intergovernmental Panel on Climate Change, has reduced its global warming predictions for the year 2100. We don't think the Earth's temperature is going to go up by 3 degrees anymore. Data over the past 20 years has made us believe that it's probably going to rise by only 1.3 degrees Celsius. So I don't think we're going to see these catastrophic effects that you maybe would have seen if you had watched the movie An Inconvenient Truth, which made things look like things are going to be really bad. So the original IPCC prediction was that with the line going straight up there to 3 degrees, that's what they thought was going to happen. But because from 2000 to about 2015, global warming actually stopped and the temperature on the planet was actually cooling, they've realized that there's this cyclical effect on the temperature of the planet, and more models now have predicted more like a 1.3 degree rise at worst, maybe even less than 1 degree temperature rise. We'll just have to see how that goes. But at least we don't have to worry about, at least at this time, the really catastrophic effects of burning fossil fuels as they maybe had thought 30, 40 years ago. Now, if you are an environmental scientist, you should really be familiar with this person, Bjorn Lomborg. He's actually an economist, but he's a green activist. And he takes things from a very quantitative point of view and analyzes the effect of every policy move that any country or any world organization wants to do in terms of mitigating global warming. And he suggested that instead of doing what California is doing, where we're trying to make fossil fuels so expensive that nobody wants to use them, or subsidizing today's inefficient green technologies, the technology for solar panels right now is not really great. And so if you wanted to put solar panels on your house, it would cost a lot of money. And so what California does is they subsidize that. And so I wasn't going to put green solar panels on my house until I found out that you were going to help me pay for it. And so I decided that seeing how you were going to pay for a significant amount of my solar panels, I went ahead 5 years ago and I bought them, and I now have solar panels on my house. But if you weren't going to help pay for that cost, they're so expensive. Really, the only people that would have them would be really, really rich people. And most everyday people wouldn't be able to afford that. So Lomborg doesn't think it's a good idea to try to increase the price of fossil fuels to stop you from using them. I mean, that's going to really be bad for poor countries, and they're not going to be able to actually improve their economy and get their people out of poverty. And really, you can't run all of your energy on inefficient green technologies if it really costs a whole lot of money. Germany found out that retired people were turning all their lights off during the night because they couldn't afford the electricity that was being produced by solar and wind energy. So what Lomborg says is we should boost our green energy innovation by raising the annual global green energy research and development money from about $15 billion a year we spend to $100 billion, significant increase. So spend a lot of money, giving it in small grants, 100, 200,000 at a time, to different companies or universities, and let them try to work on green technology to make it more efficient and more cost effective. Bill Gates is already involved in this. He gave UC Irvine a grant to work on this. They've got people at UCI. They're now creating devices that actually absorb carbon dioxide out of the air. So that means if we continue to burn fossil fuels, this type of technology could actually just reduce suck the carbon dioxide out of the air, much like the scrubbing is done in those coal burning power plants. So this could be used in a lot of different ways to actually alleviate the problem of having an increased amount of carbon dioxide in our atmosphere. So why would we want to do this? And this is always an important thing in Lomborg's thinking. Well, it'll lead to the green energy being more cost effective. And if something's more cost effective, you're going to buy it. That's when you guys all decided you were going to pay for half of my solar panels on my roof. I said, okay, I'm going to buy them now. Secondly, it'll actually leave money to combat other things. If we're not spending $250 billion a year as a country trying to prevent global warming or trying to postpone global warming by 4 years, and out of that $250 billion, we spend $100 billion on research and development, there's a lot of money left over. That could combat a lot of other things that are happening on this planet that are also bad: poverty, malnutrition, poor sanitation, tuberculosis, malaria, corruption, pollution. It's been calculated that the projected annual deaths from global warming on this planet as we approach 2100 would be maybe 250,000 people a year, which is horrible. But what are the deaths due to all of these other things? Projected annual deaths from all the other causes are 26 million a year. So I don't know, to me, it just makes more sense that if we're going to have a big chunk of money, it may not be put to the best use by using it to delay global warming by 4 years, but maybe we can try to improve research and development to lower the cost of green energy and then use some of that money to help raise people out of poverty and then improve sanitation around the world and pollution.